right? And that section is actually how do we discuss about the different movements of the stars on the sky, which is what we did not talk until now. Now this is something very interesting. So let me share my screen. Right. So I guess all of you can clearly see the shared screen with you. Let me have this. Right. Yes. And so what I'm going to discuss with you today is how these different stars move on the sky. Now, if you go outside, then look at the sky, let's say for 3 or 4 hours at night, starting, let's say, from 7 p.m. at night, what you will observe is actually all the stars are moving. They are moving from east towards the west side, right? So that's usually what happens. And if you take, for example, the sun, so the sun rises from the east and it will again set from the west side. Now, for you actually who are located very close to the equator, so this is mostly true for all the other stars as well, which is not the case for the countries like USA, which is where I am located right now. So the story is different. If I go outside and look at the sky right here in this area, also you don't see that much, but you will see there are certain stars that they never rise or set. I think we discussed about this at the very early stage in our class. So there are certain stars, they are actually just circling around a certain point, right? And they never rise or set. And these stars are called the stars who are within the circumpolar window, and we discussed about this earlier. Other than that, usually the stars rise from east and set from the west. And also you can see these different star patterns in the sky, right? And if you look at, for example, now in these, for example, a constellation like Orion constellation, you can, if you look at the Orion constellation, the constellation itself, you will see clearly that all these the patterns of the stars or the set of the stars will move from one direction to the other direction, but they will preserve their pattern, right? So the Orion constellation has a certain pattern in the sky, and that pattern will be preserved, right? So it will not change. So you will go from east toward the west side. That shape of the star pattern will not change. It will be the same. So it will go from left to from east to the west side, which will not change. And however, now this raises a question actually whether these stars, that means the relative motion between the stars, you cannot see it, right? Because that pattern that you see, it preserve the pattern and whole the system will move from this side to that side. That's what we usually see in the sky. But actually this is not true, because for the stars, they actually move across the sky with respect to each other as well, but their movement is very, very small compared to, with respect to one another. And because of that, for a short period of time, you cannot, detect that small movement, right? So that's actually what happens. But in this particular chapter, what we are going to discuss is about that motion of the stars on the sky with respect to each other. Even though that's very small motion, we can still see there is a motion. So we are going to discuss about that, plus a little bit about the binary star systems, right? Now this remind me that there will be a, I guess, a lecture organized by Geophysics Society on this next Tuesday, which will basically give you a good idea about, I mean, that I think all of you should participate for that lecture as well. So I will have a post that I will consider that as a part of this lecture series as well, right? So there may be 1 or 2 questions that could appear from that lecture. So we consider that as an extra guest lecture. So make sure that you also participate for the, so I will take that as a class lecture as well. That will teach you the practical side of astronomy, basically. So which means, so this will be, the lecture will be done by Professor Tilina, and he will basically talk about how practically how you do an astronomy research, which is an important part that you should actually learn, so that you can get an idea. He will not go into very deep things, but he will discuss basically how you start a research in astronomy and how to, how you can take data and how you do the basic analysis, not the analysis, but how you do it, right? So make sure that you participate for that. And that will be also considered as a section for this lecture series as well. So I will probably have a separate post for that as well. And so I think he will also talk about these binary star systems in there. What are binary star systems and how you use, how you take measurements for the binary star systems using a telescope, right? And right, so let me go into this section now. Right, so this is what I have discussed. The stars usually appear to be fixed in their relative positions. However, this is an illusion caused by the very large distances to stars. So that's what you see usually when you look at a star pattern. You will see that these stars are kind of, fixed in the sky, but they are actually not, right? So they are changing relative to each other, but that change is not, obvious. That's one reason is that these are at very large distances, right? However, the stars actually move with respect to each other and change their relative positions. Now, one way to actually look at or observe whether these stars are moving on the sky is actually look at the Doppler shift of the stars. Basically, you know what Doppler shift means. When you have a set of spectral lines, if you have a star moving towards you or moving away from you, there is a shift in the spectral lines. So this is what we call it as the Doppler shift, and this is very similar to the Doppler shift in sound that you usually use to study in your first or second year of your studies for physics, or even in A levels, right? So you know that if there is the sound, if that goes away from you, the sound kind of decrease. If a particular vehicle is coming towards you with a siren or something like that, you hear an increased frequency of that sound, right? So that's how you talk about this Doppler velocity, right? Sorry, the Doppler shift of sound, and the same applies for the Doppler shifts of light as well. So if a particular object is moving away from you, you will see a shift of the wavelengths or shift of the colors basically. And what usually has is there is a red shift, because if something is moving away from you, so it will shift into the longer wavelength. So that it means you will observe a Doppler red shift. If something coming towards you, that means you are observing a Doppler blue shift, right? So that amount of shift, if you can measure that amount of shift in the spectral line, you can basically use that to calculate the radial velocity. So that means how fast a particular object is moving away from you, or how fast a particular object is moving towards you. You can calculate that, right? Right. Now, so that's one kind of motion that you can actually calculate. So that we call that as a radial motion. Because from the Doppler shift, what you can actually calculate is whether a particular star is moving away from you or moving towards you with respect to your line of sight, right? So that's what you can calculate. And apart from that, when you look at certain stars, there is a change in the relative position of the stars on the celestial sphere as well. So that means you don't consider whether a particular star is moving away from you or move towards you. Rather than what you look at is whether that particular star is moving across the celestial sphere, right? So you don't consider the distance changes, whether it's moving away or moving towards you, but on the celestial sphere, whether a particular star is moving across the sphere, right? So this is a one good example. Basically, this is the movements perpendicular to your line of sight. So that means on the celestial sphere, whether a particular star is moving towards or away from you. And so one of the very great examples for this is Barnard star. So the Barnard star is basically considered as a star that has the largest proper motion, right? And if you look at this particular, there are three photographs that I have here. And if you look at the photograph A, and there is a one bright star right here. I guess you can see what I am marking down here. This particular star right here, and this is the Barnard star, right? This is the Barnard star. And after 10 years, you can see that while all the other star patterns are kind of similar, and that means they are not changing that much. However, this particular star is moving, and you can see there is a star pattern right here. So it has not changed. When you go for the same field after 10 years, that star pattern is there. I mean, it will change a little bit, but not that much visible. But the Barnard star is now right here, right? And then in 2005, the Barnard star has moved to this position. And you can clearly see that this star right here has not moved that much. So it's kind of in the same position for this span of 20 years. But the Barnard star has moved. In 1985, it's right here, and in 1995, it's right here, and 2005, it has come up to this position, and clearly you can see that there is a movement for that particular star. And it is that this kind of movement that we call usually as the proper motion of a star. So that means the movement across the field, right? And the way that you capture it from images like that, if you take the same field imaging after so many, I mean, at different time periods, if there is a star that is moving compared to the other stars, you can clearly catch it. Now you can see that these changes are very slow actually, right? Even though you detect it from a photograph like this, it is not easy to detect this kind of small changes by looking at the stars on the sky, because this doesn't happen in an overnight, right? And this particular star, which is the Bernard star, is the one that has the largest known proper motion. And usually it takes 200 years to change its position in the sky by an amount equal to the width of the full moon. So the width of the full moon is usually kind of an half a degree, right, in terms of the angle. So it's half a degree. So if you need to change that amount on the sky, it will take 200 years. So that's why these kind of motions are hard to detect, right? Now, what you need to understand here is the particular star can have two kind of motions. One is the radial motion, which means it could go towards, the star can come towards you, can move away from you. And that is what we call radial motion, which is usually measured using Doppler shift. And then star could have this proper motion. So that means the motion across the line of sight. And that motion is what we call as a proper motion. And if you, for an example, here is another example that change of the star patterns due to the proper motion. And this is one of the famous constellations that you will see up in the sky, which we call as Big Dipper. And the top picture that you have here is how this particular constellation, or the shape of the constellation, looks like 50,000 years ago. Right? How it looks like 50,000 years ago. And today, how it looks like is shown in the center picture, right? And I have put some arrows there, that those arrows are basically represent in which direction the stars are usually moving, right? So due to its proper motion, but that motion is very, very slow. You will not see the change in the constellation pattern. Probably over the course of your lifetime, you will not be able to detect it. You can see that on the last picture is how the shape of the constellation looks like after 50,000 years. And you can clearly see that there are some changes, right? So this means that these constellation patterns that we imagine that they are fixed on the sky will change their shape over a very long period of time. For example, you can see this small change of the constellation pattern has taken around 50,000 years, right? So that's the time span. So you can see that this radial, the proper motion is a very, very slow effect, right? And right now, if I combine this whole story to one image, this is what you can see. For the motion of a star, there is sun right here, and there is another star right here. And so this star, what I have discussed up to now is this particular star could move either away or towards you. And here, with respect to the sun, this star could move away from you or towards you. That is what we call as the radial velocity, and that can be measured using a Doppler shift, right? And then there is another motion, that is this change in the angle across the line of sight, right? So across the field, you can see the change in the position of the star, and that change is usually measured from this angular scale, right? So basically, this is the measurement of the proper motion will be this angle, which we call as mu here. So basically, this is measured in terms of degrees, right? Like how many degrees it will change per 1 year. So that's how you usually measure the proper motion. But the radial velocity you can measure, right, from the Doppler shift. And if you combine these two measurements together, then you can get this space velocity. There are two motions, radial velocity and the transverse velocity. Transverse velocity is usually calculated by converting the proper motion into the transverse velocity, which is not hard, right? So we know this, this V equal R omega equation. If you know the angle or the speed that it is moving across the field, that is how many arc seconds or arc minutes or maybe degrees per year, maybe you can calculate that it is moving, and you have the distance between the sun and earth, so you can multiply this by d to calculate the transverse velocity. So once you have these velocities from the same units, you can adapt those two vectors as vectors to get the space velocity. So that's how you usually do the calculation, right? So make sure that you understand this. I have mentioned here as well. So usually what astronomers measure is the proper motion, right? Proper motion is this angle, which is the change in the apparent direction of the sky measured as fraction of degrees. Now, if you need to convert this change into a speed, let's say kilometers per second, then what you need to do is you need to get the distance from the sun to the star. So you need this distance, and then you have to multiply it by this angle by converting it to proper units, right? So that will give you the transverse velocity. And then you can combine that with the radial velocity to get the space velocity, right? So that's what I have mentioned here. So if you need to know the true velocity, true space velocity of a star, so you must know the radial velocity, proper motion, and the distance. So there are three things that you should know. The radial velocity, which can be measured using the Doppler shift, the proper motion, so that is that angle that you have to measure, the angle across the field, and then the distance to that particular star, right? And then the star's space velocity can also, over time, cause its distance from the sun to change significantly. So that's obvious, right? So there will be small change with the sun as well. But it's a small change that you get usually for a smaller period of time, but over hundreds of thousands of years, this change could be significant, which will even if affect the apparent brightness of the nearby stars as well. And there is one example. The star Sirius in the constellation Canis Major is the brightest star in the sky. So that is the Sirius is the brightest star. However, if you think about 100,000 years ago, it is the star Canopus in the constellation Carina was the brightest star, right? And little over 200,000 years from now, Sirius will have moved away and faded somewhat. And the Vega, the brightest blue star in Lyra, will take over its place, as the brightest star in the year. Now you can see how this the motion of the stars affect even for the brightness, because the apparent brightness depends on the distance to the star, right? So we usually assume that these distances are not changing because we don't consider about this proper motion and the radial motion of a star. However, if you think about a very large period of time, like 100,000 years, 100,000 years ago, it is not the Sirius actually the brightest star. It is the Canopus. So there is another bright star called Canopus in the sky. It was the brightest star because of those distances are changing over the period of time. Now, around 200,000 years from now, which is a very large period, the Sirius will not be the brightest star at that time. So we will have a different star, right? That is the Lyra. So these stars are also visible in the sky and also bright. But in today, the Sirius is the brightest one, but after 200,000 years, Sirius will not be the brightest one, right? that will be the brightest one will be the Vega star. Lyra is actually the constellation that it belongs to. So the Vega will be the brightest star. So that happens due to this movements of the stars on the sky. Right. So that is one kind of motion that could happen to a star. And then there is a second type of motion, that is the rotation of the stars. Now this is also important. There are stars that rotates its own axis, right? And anybody knows whether the sun rotates its own axis, so how much it takes, how long it takes for the sun to complete the cycle? We kind of learn about this in the lecture, so just go and check what happened to our sun. But the rotation of stars means actually the star itself rotating around its own axis, right? And the how fast it rotates is different for different stars. Now, what I am focusing here is how do you measure that? Because all the stars, you cannot go to the star or bring the star here to make these measurements in laboratory, right? So which is possible in our day-to-day life for some of it, but for the stars, you cannot do that. So you have to be very smart here. If you need to make a measurement for these kind of stars, like how fast that they are rotating, you need to be very smart and have to apply science differently. So this is still the knowledge that or the things that you already know, right? So we all know about the Doppler effect, and now you have seen that even to measure the radial velocity, you use the Doppler effect, right? Actually, you can use the same technique to measure the speed of a star. The speed means how fast it is rotating, right? Not how fast it is moving. If you need to measure a particular star's rotational speed, you can use the Doppler effect. Actually, what happens is when you take a star, it's an object. It's not a point-like object. It's a kind of a huge object. So when a particular star is rotating, one side of the star is moving away from us while the other side of the star moves towards us, right? So what that means is if you look at the spectral lines, the side that is moving away from us will have a red shift, while the side move towards us has a blue shift. And if you look at the difference of these two lines, or the width of these two lines, you can actually measure or get an idea about the speed or the rotational speed of the star. The idea is, if you have a particular star that is rotating very rapidly at a greater speed, what will happen is you will have very broader spectral lines. So that means one side is moving so fast away from you, and the other side is move so fast towards you, right? So that amount of shift, blue and red shift that you will get, the difference will be very large, right? So this effect is actually called as line broadening in astronomy. And the amount of broadening of the line will tell us the speed, right? If the line is more broader, so that means this star is rotating faster. So it is something like this. Now here is a picture. I hope you can see it. Right, so here is a star that is not rotating. So what you will have is, there is a absorption, there is a one line right here, the dip, right, shows you the luminosity. So there is the dip in the light curve. However, if the star is rotating, this side is moving away from you, this side is moving towards you, and this line get broader. Right? So this dip get broader. So that's because of the star is rotating now. And this is what we call as a line broadening. And if this rotation is very fast, this line will get even more broader, right? So then you will have more, wider dip like this. And this is how we identify the rotating stars and non-rotating stars. And also, if the line becomes broader and broader, that means the star is rotating more fast and fast, right? So that's how you identify it, right? Right. And here is an example of this rotation of the stars. As you can see, the star Altair is one of the brightest stars that you will see up in the sky. The rotation period is 6.5 hours. That means for every 6.5 hours, it's changed its axis, and it's rotating faster, right? And if you take our own sun, usually the sun has a rotation period of 24 to 30 days, which means it will rotate our own axis for every, let's say, for every 30 days, right? It's kind of slower compared to the Altair. Now, I have a question for you. Which of these stars will have more broader spectral line broadening? So which one will have a higher width for the line broadening? Let's put it in that way. Is it Altair or the sun? Now, if you understand what I told up to now, you should have an answer, right? What will be the answer? So I got one answer as Altair. Is that everyone is agreeing with that? Or he is the only one who knows the answer, whether it's right or wrong? What do you think? Is that answer is correct? So I want to have comments from the others as well. Right, so just one says agreed, so which means I assume that there are at least 6 of you, so all the others do not agree with his idea, right? So there is only one who thinks that the Altair is the fast rotating one, which is correct actually, because the faster you rotate, then you have line broadening should be larger, right? So you should understand these kind of things actually. Right. So those are the two kinds of rotations. I mean, two kinds of motions that we can have for a star. And let me go into the next section now, which is about the binary star systems, right? The binary star systems means actually the stars that you see up in the sky actually, most of these stars we see as a part of multiple star systems revolving around a common center of mass. So usually most of these stars that you see are actually binary star systems, or maybe there are more than 2 stars, right? However, if there are 2 stars in the system, we call those as binary star systems. And there are different types of binary star systems. And one type is called visual binaries. That means they are very close to the Earth, so that you can very clearly see there are 2 stars individually from a telescope. When you look from a telescope, you can see there is one star and there is another star rotating around it. So if you can clearly and visually see that, we call those as visual binary stars, right? And if you cannot see it in that way, However, you can detect that there is another star by using a calculation. That means you cannot see both these stars. However, you can have a detection for this unseen companion binary star because of the gravitational influence by the other primary star, right? So this method is useful when you have a binary star system too far away. So that you cannot identify there are two stars. However, the stars are very close to one another, and one star is very brighter compared than the other one. So if you have this kind of situation, you can actually identify it in this way, because you cannot see one particular star, but you can see one star. But however, that the star is affected by that surrounding star due to the gravitational effect. And these kind of stars we called as astrometric binaries. And the third one, what we called as the spectroscopic binaries. So that means there are the both stars will appear as a single star when you have a photograph. However, if you look at the spectroscope of the system, you can clearly see there are two stars. And this is called spectroscopic binaries. The way that actually you see that there are two stars is in this way, right? Because if there are two stars, both stars are moving, let's say B moves to this direction and A moves to this direction, you will see A and B, two lines here in the spectrum. If they are moving into perpendicular directions, there is no relative, change in the effect in the two lines. So the two lines will be, coincide like this. And when the other side happens, when the B star moves towards us and A is moving away from you, these two spectral lines will be shifted. I guess you can understand it, right? So this is kind of the same effect that you get in the line broadening as well. I mean, the effect is similar, but the way that we use at different locations is different, right? And this is called spectroscopic binaries. And you can actually look at the radial velocities as well, because when you know the shift of the Doppler shift, you can actually calculate the speeds, right? And then there is the fourth type is called as the eclipsing binary. If there are two stars, one is passing in front and behind the other star, we call that as an eclipsing binary, right? So this is the same word that we use for the solar eclipses and lunar eclipses. For the same reason, one object covers the other one. And here also, there are two stars. One star covers the other star. And we call that as an eclipsing binary star system, right? So what happens is actually there may be one large star and one smaller star that goes around each other. And when this one particular star comes in front of the other one, you will lose some of the light coming from the star system because one covers by the other one, right? So then you will see the loss of light. But when you have an orientation where both stars can be light from both stars can be seen or detected together, then you will get the maximum brightness for the system. So we call these kind of curves as light curves. And this is an example. So you can see that there is one larger star from the red color, that is star number 2, and then there is one small bright star, one from the blue color. It goes around the brightest star, and you can see that at position 1. So that means this position, you can see the blue star is not covered by the red star. So basically, you can see the light coming from both stars, right? So you will get the maximum brightness. However, at position 2, you can see that the smaller star is behind the red large star, and then you can see the loss of light. And then at position 3 again, you can see when you look from your side, light from both blue star and red star will be visible, and you can see the complete amount of light. So you will get the maximum light again. And position 4, you get the blue star at the front side, red star in the back side. So that means basically this blue star is in the front side and it covers a small portion of the red star, right? And you will lose some of that light. So that's what the position 4 is. And these kind of curves are called light curves that basically explains you how the brightness of a system change with the time, right? So that's what we call as a light curves. And I will have a question for you to think about, and this will be explained here in words here in the text as well. When you have this blue star covered by the red one, right? You have a larger loss of light. The loss is huge compared to this fourth orientation. That means you have a blue star on the front side and a red star in the back side, right? So just think about why that happens. So that's a good thing to study. So I'm not giving you the answer, but you should know about it, why that happens, right? So this is basically by thinking about the Stefan Boltzmann law, where the brightness of a star depends on two things, that is temperature and the surface area. You can think about this, right? Which will be more effective. Right. Now, one last slide, which is very important, but we could not discuss in the previous lectures, is the mass luminosity relationship of a star. And the most, so this is not related to binary star systems, by the way, this is something extra. For the most stars, the mass and the luminosities of a star are actually, there is a relationship, right? Basically, the more massive the star, the generally it is more luminous. And this relationship is what we call as a mass luminosity relationship, which is shown in this graph. And on the right hand side, you can see that there is an important relationship as well. That's how the luminosity and the mass is related. Basically, luminosity is roughly equal to the fourth power of the mass. It's the rough relationship. So make sure that you have that idea with you. And here are two examples. There are two stars that differ in mass by factor of 2. Then the more massive star will have 16 times brighter compared to the smaller one, right? So I guess you get the idea, right? So this is called mass luminosity relationship. Even though the equation said it's the m to the power 3.9, we usually assume that it's roughly the fourth power of the mass, right? Right. So this is the very last section that I want to discuss with you about the stars. So while I am starting to sharing the story about the galaxies, let me know if you have any other questions. Okay, so maybe let's do it in this way. I guess this is a good point to stop the lecture, because we are going for a completely new series of lectures. And we will start talking about galaxies from the next day, right? And for the assignment that I have assigned about the supernova explosions, I can see that only one of you have completed and submitted it. So make sure that all the others also try it, right? So what my